Hey guys, it's Miss Maneely, and I'm going to go through the review for our Chapter 7 Sampling Distributions Assessment, which is going to be next class. The first thing I want to do is sort of just recap again the different settings that we're going to have on the test. This kind of really pulls everything together that we've done all year. If you remember, there are essentially two types of variables. We have quantitative variables, and we have categorical. Okay, with quantitative, the variables are always going to take on numeric values, and it makes sense to calculate a mean for those values. With categorical, sometimes they can be numeric, but it won't make sense to take an average. Like zip code, for example, is not going to make sense to take an average, so it's considered categorical. Oftentimes with categorical, we're looking at the count of successes or the proportion of successes in a sample. With quantitative, very often you'll have a description of a population distribution. So sometimes you'll be given the mean or the standard deviation. Not all the time, but a lot of times you'll be given something. You'll also be given like the shape of the distribution, but again, not all the time. But you may be told, for example, that the population is bell-shaped and symmetric or normal or skewed. With categorical data, there is no population distribution because remember, there's only two outcomes. So if I were to graph them, I'm going to have a bar graph. That's basically going to have two bars. One bar is going to represent the frequency of successes, and the other is going to represent the frequency of failures. So talking about the shape of the distribution doesn't make any sense. We only talk about shape when we're dealing with quantitative data, and we can only do that with populations when we're dealing with quantitative data. Okay, I want to distinguish between how to handle situations when you have small samples versus when you have large samples. So if we're looking at sampling, one item or one individual versus sampling many. And when we're dealing with categorical, oftentimes we'll sample a few versus sampling many. And this is hopefully going to relate what we've done with the binomial distribution as well. Okay, so I am just going to focus on quantitative data for now. If you remember in the beginning of the year, we started talking about normal distributions. So if you're given a normal population, or if you're given a scenario, if you're given a population that is known to be normal, oops, then you could say something like X is distributed normally and you'll be given a mean and a standard deviation. Then you can find the probability that X is greater than some value. I'm just going to call it K since we've been using K a lot. You can find the probability that X is between two values. You can find the probability that X is less than a value. Just don't forget to calculate your z-score. And this is basically just using the normal PDF that the normal CDF that we've been using all year. Okay, you don't have to do any kind of conversions with the mean or the standard deviation if you know that the population is normal. Just remember that X represents a single individual, single item or person. When we started talking about sampling distributions, now we're talking about the mean of a distribution. And so when we're sampling many, instead of talking about X, now we're talking about X bar. And you need to make sure that you define X bar. So X bar is going to be the mean of the sample. And so you want to make sure you're in context. And then there are two conditions. If the population is normal, And I'm rewriting this in a way that's a little bit different than we did on your study guide, because I'm hoping that if you see it a different way, maybe some of the other items will click for you. So if the population is normal, then X bar is exactly normal. Because if the population is normal, then anything I sample from it's going to be normal, whether I'm looking at sampling a single item or sampling many. And if that's the case, I can say X bar is distributed normally. Now my mean is going to be the same as it was for the single observation, and my standard deviation is going to be sigma over the square root of n. But I'm only allowed to use this formula when the population is at least 10 times my sample size. And what I'm seeing is a lot of you are confusing your conditions. So I'm hearing a lot of people saying things like, as long as the population is more than 10. Well, think about what you're saying. Of course the population is going to be more than 10. If it wasn't, then I wouldn't need to sample at all. I would just take a look at the 10 people in the population. But what I've noticed is a lot of you are confusing the conditions. So we have two situations with means when we're dealing with quantitative data and we're dealing with samples. If the population is known to be normal, then X bar is going to be normal no matter what. The only thing you have to check is that the population is at least 10 times the size of your sample. If the population is not normal, then X bar is approximately normal. And this is if n is greater than or equal to 30. And that's another condition that you need to check. And if that's the case, then you can say X bar is approximately normal, and then it's the same conditions. It's mu and then sigma over the square root of n. But again, whenever you're using that standard deviation formula, you must ensure that the population is at least 10 times your sample size. And a lot of times you're not going to be told how large the population is, so that's an assumption you're going to be writing. So you're actually going to write, assume the population is 10 times n. And make sure you actually fill in the numbers in the problem. Don't just tell me that the population is 10 times the sample size. If your sample is 30, then you want to say, the population of cars is at least 300. Assume that to be true. Okay, and then once you've assumed that normality, and again, remember, you still want to make sure that you define your random variable. So tell me what X bar represents, then tell me how it's distributed. So whenever you're asked to describe a distribution, you're asked to tell me what probability model it could be. So is it normal, is it binomial, is it geometric? And then you need to state the parameters. So with a normal distribution, we're talking the mean and the standard deviation. If it was binomial, then you'd be telling me n and p. If it was geometric, you would just tell me p. But hopefully that kind of sorts out the situations with the sample mean. And again, you still have to calculate your z-scores. And you'll be using the normal CDF here. Okay, so let's switch gears and talk about categorical data. If we're sampling a few, this is where you want to check to see if it meets the binomial conditions or our sampling distributions for p hat. So if n times p and n times 1 minus p are less than 10, so this would mean fewer than 10 successes and failures, then you must use a binomial distribution. Okay? Be really careful here. In this case, we would say x equals the number of successes in n trials. If we're dealing with a situation where n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then use a normal distribution. And if we're going to use a normal distribution, we're going to be talking about p hat, which is going to be your proportion of successes in n trials. So the notation that you use is very important. So if I'm dealing with a binomial random variable, I'm going to need to define n and p. And the assumption that I'll need to list is independence. If I'm talking about p hat, then I can say p hat is approximately normal. And I would use the distribution where my mean is p and my standard deviation is the square root of p times 1 minus p over n. But again, if I use the standard deviation formula, so this is true for both my means and my proportions, if I use this formula, I have to show that the population is at least 10 times n. Okay? So if I'm dealing with a small sample, I can use either the binomial PDF. So if I'm dealing with the probability that x equals k, that would be the binomial PDF. Or if I'm dealing with the probability that x is less than or equal to k, I'm dealing with the binomial CDF. If I want to talk about the mean, it's just n times p, and my standard deviation is going to be the square root of n times p times 1 minus p. But if I'm dealing with a large sample, then again, my formula for the mean, and this is where you really want to be careful. So in this case, when I'm dealing with a sample of a few, this is just the mean of x and the standard deviation of x. If I'm dealing with p hat, then I need to change my notation. The mean I'm referring to is the mean of all my proportions, of all my sample proportions, and that's just going to be p. The standard deviation of p hat then is going to be the square root of p times 1 minus p over n. And so you do need to be able to distinguish between whether or not you're looking at small samples versus large samples. And the test is going to include examples of all of these. So we're going to be looking at situations where the population is normal and you're just going to be sampling a single individual from that population and having to find the probability. And then we're going to be sampling many from that population and figuring out the mean and the probability associated with it. And then we're going to do the same thing with the binomials and the sampling distribution for p hat. So it's important to distinguish whether or not, first of all, whether or not you're dealing with a quantitative or categorical variable, and then whether or not your sample is too small to use a normal, or whether it's large enough to use a normal distribution, and then answer questions accordingly. So let's just go ahead and jump right into some of the examples on your review guide. Let me move this out of the way. Okay, so in the very first two questions, this is simply identifying the difference between the sample and the population, and then the parameter and the statistic. And this is actually, it seems like it's easy, but this is where students lose points just for silly mistakes. So in number one, it says the senior class at a large high school has 438 students. The principal collected data on 36 of them and found the mean math SAT score was 462. The subsequent computer analysis of all seniors showed the true mean to be 496. So what I'm going to do right now is I'm just going to underline everything I know about the whole population. So I know that the senior class at the large high school has 438 students. I also know that the mean for all seniors is 496. Those two pieces of information go together because they're both referring to everyone. So the population in this case would be all 438 students in the senior class of the large high school. Where students sometimes lose points is just by saying seniors or seniors at the large high school. Well, how many? And this is where you really want to be careful. Are you talking about everybody or are you just talking about the sample? So be specific. Use the word all when you're referring to the population. Our sample in this case would be the other group. So let me underline this in a different color. We collected data on 36 of them and found their mean SAT score was 462. So everything that I've underlined in red now refers to my sample. So this would be my sample would be the 36 seniors selected by the principal. And notice that when I'm describing the population in the sample, I'm not referring to any of the information that was collected. The population and the sample are just referring to the who. Who was it that I was examining? Who was I trying to determine information about? It's just the who. The statistics when the parameters are the what. What am I learning from them? And in this case, we want to also confirm whether or not we're dealing with a mean or a proportion. Well, in this case, I mean, it tells us very obviously that we're dealing with a mean. Okay, and so I know that. So in terms of my parameter, if I'm dealing with a mean, I want to use mu. And so we're told in this case, and we don't always know this, we're told that the true mean is 496, and that would be the math SAT score. And so you do want to make sure that if you're dealing with a mean, that you include your units as well, because you will lose points if you don't. The statistic in this case is going to be the number that describes my sample, and since I'm dealing with means, I want to use an X bar, and that would be the 462. And again, that would be the math SAT score. Okay, so things that you would lose points for would be not having units, and not being specific about the distinguishing between your population and your sample. So if you're not telling me that it's all students in the senior class versus the ones that were selected, you could lose a point for that as well. All right, let's take a look at number 2. It says the Gallup poll asked a simple random sample of 1,785 adults whether they attended church or synagogue during the past week, and 803 responded yes. In fact, 40% of the adult population attended church or synagogue services. So let's talk about the population. I'm going to underline this in blue. So we're told the adult population is really, I mean, it tells us that we're dealing with adults in our population, and we also know that 40% attended church or synagogue, so that gives us our parameter. In red, I can see that we're looking at a simple random sample of 1,785 adults, and 803 of them reported or responded yes. So my population in this case is going to be all adults. And we can assume that this means like in the US. My sample then would be the 1,785 adults selected. Okay? And then this question is asking, does this situation involve a mean or a proportion? Anytime we're dealing with a count, or a percentage, we're often dealing with a proportion. So in this case, it's not there was an average of 803 yeses. We counted those yeses. So in this case, we're dealing with a proportion. So when I'm asked about my parameter, I'm going to be using the letter P, and that corresponds to 40% of the adult population that attends synagogue services or church services. And my statistic is going to be the sample result, P hat. Now be careful because I'm dealing with a proportion. I need to make sure that I'm telling you that it's 803 out of the 1,785. And you don't need to reduce that, but you do need to make sure that it's a proportion. And with proportions, you don't need to worry about units because it's just, a fraction or a proportion. So you don't need to worry about putting units here. Okay. In number 3, this is a quick review on the difference between bias and variability. Bias, remember, always deals with the center. Variability deals with spread. And we said that in order for our sample statistic to be unbiased, that as I take samples, I expect there to be some variation. Every time I take a different group of people, I'm going to get a different result. Some of those results are going to be less than the true parameter. Some of them are going to be more than the true parameter. But I would expect if my statistic is unbiased that it would be centered around the true parameter of the population. Ways that we introduce bias into sampling would be if we didn't take a simple random sample, or if there was response bias. So if I was interviewing students about, their habits on the weekend and people weren't comfortable answering honestly, I'm not going to get the correct or I'm not going to get the true information. So I might find that my statistics are biased. And so that's basically a systematic favoring of one particular outcome. Variability is not what's the word I'm looking for? Isn't very detrimental. I mean, we expect it. Variability isn't a bad thing. We can reduce variability by increasing our sample size. Bias, though, can be devastating to our data. If there's bias introduced, whether it's in our selection process or in the method that we've used to collect the data, bias could destroy our data. So if I take a look at letter A, so notice that in each one of these cases, the population parameter is this little arrow. So that's where the center of all my distributions, if they are unbiased, the center of my distributions should be there. So if I look at letter A, if I look at this curve, the center of this curve is actually here. And so since it's not centered around the population parameter, I would say that this has high bias. And when I compare the spread to the other distributions, for example, the one below it, I can see that it's more spread out. So this situation also has high variability. If I look at letter B, notice that my distribution is centered around the population parameter. This tells me that there is low bias. Since the distribution is not as spread out as the one below it, I would say that this also has low variability. In letter C, this is a situation where it's off-center, so this tells me it's high bias. But in this case, it's not very spread out, so there is low variability. And in the last one, it's centered appropriately, so this tells me that there is low bias. And compared to the one above it, there is high variability. Okay, so when we're thinking about like the best case scenario, this is the situation that would be best. The worst case scenario would be letter A because it's off-center and it's got a lot of variability. So the best case would be letter B. Okay, so let's actually go ahead into some of our calculations and practicing using the normal distribution and interpreting problems. I'm going to actually shrink this a little bit so that I can also include my calculator. And so we can do some of these together. Okay, so number 4 says, just before a referendum on a school budget, a local newspaper polls 400 voters in an attempt to predict whether the budget will pass. Suppose that the budget actually has the support of 52% of the voters. The first question I want to ask myself is, am I dealing with means or proportions? And I think this is a dead giveaway. As soon as you see something like that, that's an indication that I'm dealing with proportions. And so notice that I've got a poll of 400 voters. That gives me my N. So I'm just going to jot down the information that I'm given in the problem. I also know that the budget actually has the support of 52% of the voters. That's describing the whole population. So that's going to be my P, my population parameter, which is going to be 0.52. Do not forget to change your proportions into decimals. So that's the information that I'm given. In letter A, it says to determine the mean and the standard deviation of the sampling distribution. So if I'm dealing with the sampling distribution, and it even tells me of the sample proportion, that means I'm dealing with P hat. So let's just go ahead and define P hat. P hat will be the proportion of voters in the sample who support the budget. Just like we did in the beginning of the year, anytime you're dealing with a variable, you need to define it. So I'm defining P hat as the proportion of voters in the sample who support the budget. Now notice, in this case, I am not even going to look at the binomial distribution because it is telling me to calculate the mean and standard deviation for P hat. Okay, so the mean of P hat, if you remember from the other screen, the mean of P hat and the standard deviation of P hat, that's these formulas. And remember, we also have a condition, which is to check to make sure that the population is at least 10 times my sample size. So let's go back over to that problem. So the mean of P hat I know is going to be P, which is 0.52. The standard deviation of P hat, that's going to be my P times 1 minus P over n. So 52% times 48% over, what is it, 400. Okay, I'm going to go ahead and calculate that. So we've got 52% times 48% divided by 400. Whoops. Okay, and I have a standard deviation now of 0.0249 or 0.025, I think. Okay, now I also have to state assumptions and verify conditions. The only condition that I need to verify here has to do with my standard deviation formula. And I have to check to see, is the population at least 10 times my sample? So my n, and make sure you plug in the actual n value. Don't just tell me that it's greater than 10n. Plug in the 400. So my question is the population greater than 4,000 voters? And you can just say assume this is true. Okay, so assume the population has more than 4,000 voters. We're talking about a local newspaper, and so if I'm thinking about just the local voters, sorry, there's a fire drill. apologize. I just realized that my board did not pause. So hopefully you were smart enough to fast forward through the fire drill and continue on. All right, so in letter B, it asks, can a normal distribution be used to model the sampling distribution of p hat? So this is where we have our second set of conditions. And since we're dealing with a proportion, this is where you check to see your n times p and your n times 1 minus p. And so in this case, I know that n is 400 and p is 0.52. And if I'm doing it for my number of failures, I'd have 400 times 0.48. All right, so 400 times 0.52. All right, that gives us 208, which is clearly greater than or equal to 10. And this would be 192, since the total has to be 400. And since that is clearly greater than or equal to 10, then what I can do is say that p hat is approximately normal. Okay. And then in part C, now it's actually asking for the probability that the newspaper sample will lead them to predict defeat. So it's not actually giving you a sample value to compare to. But if you think about what it takes to win or what it takes to lose, you need to have at least 50% of the vote. So to predict defeat, that would mean that the sample value would be less than 0.5. So we're looking at a probability of having a sample proportion that is less than 0.5. Because we're using a normal distribution, I need to change this to a z-score. And so again, I'm just going to be doing my 0.5, my observation minus the mean, which we said was 0.52. And then we need to divide that by the standard deviation, which we said was 0.025. And so that gives me a z-score of negative 0.8. And so now if I use my normal CDF, because I'm using my normal distribution, my lower bound, since I'm looking at a less than, my lower bound is going to be negative infinity, so negative 9999999. My upper bound, well, depending on if you're using p hat or z, I'm going to go ahead and use my p hat values. So my upper bound for p hat would be 0.5. And remember, when you're dealing with p hat, all of the numbers you use related to p hat should be between 0 and 1 because you're dealing with a proportion. My mean of this distribution, we said in part A, is 0.52. And the standard deviation of this distribution, again, what we said in part A, is 0.025. And if we press enter, we find that the probability is 0.2119. Okay, so about 21% of the time, they're going to be predicting defeat. Because even if this distribution is true, like I said, there are going to be sample values that are going to be higher than 52%. There are going to be sample values that are lower than 52%. In fact, about 21% of our sample values are going to be less than 0.5. So if that's the sample that the newspaper takes, they're going to be predicting defeat based on that sample. So let me just highlight the things that I need to see when I'm grading, because I think this also might help. So I'm going to choose, let me find my highlighter. And okay, I want to see a definition of the random variable. So if you're just looking at p hat, you want to make sure you define it as the proportion of voters in the sample. If you're dealing with individuals from a normal distribution, you'd call it x. If you're calling it individuals from a binomial distribution, again, you would call it x. I need to obviously see all the answers to the problem. So I need to see the mean, I need to see the standard deviation, and I need to see the conditions. So in part A, there are pretty much 4 things you need to show me. In part B, I need to see the conditions, and I need you to tell me that p hat is approximately normal. When it comes to the probability section, I want to see the notation in terms of p hat. I want to see the z-score, and obviously I want to see the probability. So pretty much everything that I've written here is what you need to demonstrate on your test in order to get full credit. Okay. Let's take a look at the next problem. This is number 5. It says, assume the duration of human pregnancies can be described by a normal model with a mean of 266 days and a standard deviation of 16 days. So there are a bunch of things here that clue me into the fact that this problem is dealing with means. I'm given the description of the population. So this is telling me that the population is normal. That's good to know. I'm also given the mean and the standard deviation of the population. So if I'm dealing with just the population, if I say, x equals the length of a single pregnancy, I called it x bar, but I meant to say x, sorry. So if x equals the length of a single pregnancy, then I can say that x is distributed normally. This is given with a mean of 266 and a standard deviation of 16. Okay, now that I have that in part A, where it's asking what percentage of pregnancies should be less, or I'm sorry, should last between 270 and 280 days. Again, I'm looking at single pregnancies. And so I'm dealing with just a single observation. So the probability that X is between 270 and 280 days. So this is back to what we did in the very beginning of the year. I still need to calculate my z-scores, and I'm not actually going to do that calculation with you. I'm just going to go ahead and list the z-scores. So my lower z-score is going to be 0.25, and my upper z-score is going to be 0.875. And then I'm going to do my normal CDF. I will go ahead and do this calculation since it's a little bit different than the last one. I'm using a normal CDF, but this time my lower bound and my upper bound are defined. I'll go ahead and use my z-scores this time. So my lower z-score is 0.25, and my upper z-score is 0.875. And since I'm using my z-scores, I'm going to use a mean of 0 and a standard deviation of 1. And I get that my probability is 0.2105. Okay, so that's the probability that a single pregnancy lasts somewhere between 270 and 280 days. And again, well, I'll go back and highlight everything later. Let's take a look at letter B. It says, at least how many days should the longest 25% of all pregnancies be? And again, I'm talking about my population here, all pregnancies. So if I'm looking at this time being given the percentage, I know this is 200, I know my center is at 266 days, and I'm looking at the top 25%, and I'm trying to figure out what value on my axis corresponds to that top 25%. Well, anytime you're given the area, you have to use your inverse normal operation on the calculator. So I'm going to go into my second distribution, but this time I'm going to choose my inverse normal operation, or my inverse normal command. What you need to remember, though, is the area that you enter has to be the area to the left. Let me show you what would happen if you put in the 25%. So this isn't the correct answer, but let me go ahead and put it in so you can see what would happen. And because the z-score is required, you do need to calculate the z-score. Notice how that number is negative. I can see very clearly on my number line that that question mark is to the right of 266. So 266 corresponds to my x scale. The z-scale, if I wanted to write that below it, the mean would correspond to 0. So I can see just from this picture that my z-score should be positive. So if you get a negative value, that should be a clue that you've made a mistake somewhere. So now if I go back and do the inverse normal command with 75% area to the left, that's going to give me the correct z-score. And so the z value I get is then going to be the positive value. So I know that my z-score is equal to 0.67, let's say 45. And now that I know that, I can use my formula where z is equal to x minus the mean over the standard deviation to actually solve for x. So that tells me 0.6745 is going to equal the x value that I don't know minus the mean of 266 divided by a mean of 16. So if I take this value times my mean of 16 and add the 266, I will get my x value. Notice that that's more than the 266, which is what I would expect. So at least how many days? At least, let's say, 276.79. For the top 25%. Okay, and notice that I included the units here. Very important when you're dealing with means. All right, let's take a look at letter C. It says, suppose a certain obstetrician is currently providing prenatal care for 60 pregnant women. Let Y hat represent the mean length of their pregnancies. So in this problem, your random variable is defined for you, so you don't have to write it again. According to the central limit theorem, what's the distribution of the sample mean of x bar? Specify the model, the mean, and the standard deviation, and state assumptions and verify conditions. All right, so since I'm looking at an n of 60, and I know that that is greater than 30, then I know that y bar is approximately normal. Now I know that y bar is actually could actually be exactly normal because it tells me in the very top that the population is normal. So you can even say is at least approximately normal. But I know because my sample is large enough that y bar is approximately normal. Now I can go ahead and find the mean. So I'm going to say the mean of y bar has to be the mean of my distribution. So if we go back, let's go back to that first slide where we kind of laid everything out. Since I'm dealing now with a large sample, that's this column, I know that my mean is just going to be the mean of my population, and the standard deviation will be sigma over the square root of n. Okay, so the mean of my population is 266 days, and the standard deviation of y bar is going to be 16 divided by the square root of n, which we said is 60. And if I do that calculation, then my standard deviation becomes 2.066. And again, I want to include units here. All right, and because I use the standard deviation formula, I have to assume that the population of women is at least 10 times 60, or 600 patients. Okay, and so I'm assuming that this doctor has at least 600 patients. Okay, so that answers all of the questions. The distribution itself is approximately normal, and then I'm telling you all of the different parameters for that distribution, the mean, the standard deviation, and I'm checking all of the conditions and stating my assumptions. In letter D, it says, what's the probability that the mean duration, so now I'm talking about y bar, the mean duration of the 60 women is less than 260 days. So now I need to make sure that I change my notation. I'm not talking about a single person anymore. Now I'm talking about the mean of my sample. And I'm trying to find the probability that y bar is less than 260 days. So now I'm going to change that to a z-score. I'm going to take my 260 minus the 266 and divide it by 2.066, and that's going to give me a z. So notice, even though I'm dealing with a sample mean, when I convert it to a z-score, it's the same process. And that z would be a negative 2.905. And if I, again, do my normal CDF, I should get 0.0018 as my probability. Probabilities do not need units. Okay, let's take a look at letter E. It says the duration of human pregnancies may not follow a normal model. Which direction would you expect the distribution to be skewed? This is sort of thinking outside of the box. You remember we said at the beginning of the year that oftentimes biological measures are normally distributed. But if you think about a human pregnancy, I would expect that some women are probably going to be delivering a little bit earlier than 266 days. Some women are going to be delivering, after 266 days. However, if you think about it, there are women that may give birth several weeks early. Like, there are certainly premature births, but no doctor is going to allow a woman to continue her pregnancy beyond a week or two. So you may have a baby that's born a month early, but you will not have a baby that is born a month late. So because doctors will induce labor, which is not a natural thing. So it kind of goes against what I was saying earlier about the biological measures, because doctors will often induce labor if pregnancies last too long. Last too long. The distribution I would expect to be actually skewed to the left. And that again would account for the premature births. Okay, so if the correct model is in fact skewed, does that change? Let's see if I can move this. I can't see the question. Does that change your answers to parts A, B, and C? So let's go back up to part A. In part A, my answer relied on the fact that the population was normal. So if we're saying the population actually isn't normal and it's in fact skewed, I wouldn't be able to answer that question. So in part A, my answer, I wouldn't be able to answer part A. So it couldn't be answered without knowledge of the normal distribution. If I think about my answer to question B, that also relies on the normal distribution. So that would be true for part A and B. Could not be answered without a normal distribution. But if I take a look at letter C, because my sample was large enough, I know that the distribution of sample means is going to be approximately normal. So my answers in C and D wouldn't change because of the central limit theorem. So Y bar is still approximately normal because our sample is large. So answers to C and D would not be affected. Okay, and so again, that goes back to what we were talking about on that first slide, where we were looking at small samples versus large samples. So the only way I'd be able to find probabilities with small samples if I'm dealing with quantitative data is if I knew something about the distribution. So like if I'm told that it's normal, that's great. If it's a uniform distribution, like a rectangle, and I can draw it and use the area of rectangles to find the probabilities, that would be fine as well. But pretty much otherwise, if I don't know the distribution, I won't be able to find any probabilities. All right, so let's just highlight what needs to be included in your answers for number 5. So let's see where my highlighter is. Okay, so obviously in letter A, since I'm using the variable x here, I need to define it. You're given in the problem the mean and the standard deviation, so you don't necessarily have to rewrite it, but you'll need to tell me the probability statement, you'll need to give it to me in terms of z, and you'll need to tell me the probability. In part B, you don't necessarily have to draw a picture, but I do like to see the picture. It kind of helps me understand your level of thinking. I need the z-score. And then obviously I need to see the value of x, and you need to make sure that you include units. And if it's asking for a range, make sure when you're answering the question that you give me a range. So you're not just telling me that it's exactly 276.79 days. We're talking about 276.79 days or longer to represent the top 25% of all pregnancies. In letter C, now here you're given the definition of your random variable. But if y bar was not defined in the problem, you would want to make sure that you define it in letter C. You're asked to state the mean and the standard deviation, so obviously you want to do that. Include your units as well whenever you're using a standard deviation formula. And this is going to be true for all of them, whether you're dealing with a proportion or a mean. You need to make sure that you tell me that the population is at least 10 times the size of the sample. Then you also have to be able to check for normality. And the condition when we're dealing with means is either the population is normal or our sample is large enough. And so that's what you want to conclude here. If you had said that the population is normal, so therefore y bar is normal, that would have been fine too. You just need to be able to tell me how y bar is being distributed. In letter D, you need to give me the probability in terms of y bar, our sample mean, in terms of z, and then in terms of the probability. And then in letters E and F, you want to make sure that your answers include an explanation. All right, I'm going to go a little bit faster through number 6 and 7. So in number 6, it says, when a truckload of apples arrives at a packing plant, a random sample of 150 is selected and examined for bruises, discoloration, and other defects. The whole truckload will be rejected if more than 5% of the sample is unsatisfactory. Suppose that in fact 8% of the apples on the truck do not meet the desired standard. What's the probability that the shipment will be accepted anyway? Okay, so this is one that you really have to read and understand all the information that you're given. So it says a random sample of 150 is to be selected. So that's our n value. It says the whole truckload will be rejected if more than 5% of the sample. So that corresponds to my p hat. P hat is going to be that 5%. Make sure you write it as 0.05 and not 0.5. And so it says the whole lot will be rejected if more than 5% is unsatisfactory. And we're looking for the probability that it's going to be accepted. That means that my p hat value would have to be less than 0.05. So this is ultimately what I'm trying to find, the probability that p hat is less than 0.05. Suppose that, in fact, 8% of all of the apples in the truck do not meet the desired standard. So obviously that's not known to us. Otherwise, we would just send the truck back without sampling. But if we're given a parameter, and again, that's our p-value of 0.08, now I have information that I need to go ahead and answer this question. Since I'm dealing with a sample p-hat, I need to figure out how p-hat is distributed. And so we're going to go ahead and say that p-hat represents the sample proportion of defective apples, of bad apples. Okay, so make sure you define it. I can say the mean of p hat, I know is just going to be 0.08 because that's the true proportion in the population, and the standard deviation of p hat is going to be the square root of p times 1 minus p, so that would be 92% over 150. And so if I do that calculation, I believe we get 0.022. And again, both of these values are proportions. The mean and the standard deviation relate to a proportion. Both these values are between 0 and 1. There is no need to use units here. Now, I do need to check the condition for my standard deviation formula, which tells me that I have to assume the population of apples is at least 10 times my sample. So make sure you plug in the numbers. And so we're saying that our population has to be at least 1,500 apples. And I'm just assuming, so I'm using the word assume, that that is true. The last thing I need to do is determine whether or not p hat is normal. And so this is where I'm going to double check my n times p and my n times 1 minus p. So if I do my n times p, I have 150 times my p-value of 0.08, and I know that 8% of 150 is, let's see, 12, which is greater than or equal to 10, so that condition is met. And if I do my n times 1 minus p, I get 150 times 92%, which is going to be 138, which is obviously greater than or equal to 10. And so what that tells me is that p hat is approximately normal. Okay. And if you want to go ahead then and say that p hat is distributed normally with a mean of 0.08 and a standard deviation of 0.022, you certainly can do that. Well, now I can calculate the probability that p hat is less than 0.05. But the first thing I need to do is change that to a z-score. So I'm just going to go ahead and do my sample result of 0.05 minus the mean, which is 0.08. And I'm going to divide that by my standard deviation, which is 0.022. And I get a z-score of negative 1.364. And if I do my normal CDF, I will calculate. Let's actually do this because I rounded differently on my paper. So if I do my normal CDF, my lower bound is negative infinity. That's actually on my calculator already. My upper bound, I'll go ahead and use my p-value this time. So if I say 0.05 is my p-value, or my p-hat value. Oops, I don't need the... I know the mean for p-hat is 0.08. And the standard deviation, how do I keep putting it? There we go. My standard deviation is 0.022. All right, and so if I calculate, I get 0.0863. So about 8.63% of the time, we'll accept a bad shipment. Because remember, our true proportion of bad apples is 8%, which is above the rejection amount. But we're looking for the likelihood that our sample result is less than 5%, which means that I would accept it. So about 8.63% of the time, we'll accept a bad shipment of apples. Okay. The other thing I want to point out here is how you would use a binomial distribution. This isn't one of the questions on the review guide, but there is a problem like this on the test. So what about if I completely change this problem? Let's go back for a second. And let's say instead of taking a random sample of 150 apples, let's say I take a sample of 15. Let's see. Well, actually, let's go ahead and say I take a sample of 20, because can I take 5% of 20? Will that give me a whole number? I think it would be 1, right? Yeah. All right, so let's say I take a sample of 20. So everything about this situation is going to stay the same except my sample size. So let me just kind of do this problem again, but using a different distribution if our sample was small. So suppose instead n was 20. So we're still going to keep our probability of success at 0.05. So if I think about the distribution, can I be dealing with a normal distribution if I'm talking about p hat? And so in this case, oops, I'm sorry, my true proportion would be 0.08, and I probably can't take 8% of 20 very. Let's say it's 10% so that I can actually do this problem. So I'm changing it a little bit more. Sorry if that confused you. So let's say I'm still dealing with the apples. Let's say the probability of a bad apple is 10%, and I'm taking a sample of 20. Well, I know when I check my n times p, 20 times 0.1 is going to give me 2. And since that is not greater than or equal to 10, I can't use a normal distribution here. But I can use a binomial distribution. So if I check my conditions for binomial and I say instead x represents the number of bad apples, if I assume independence between the apples and that they're not like, carrying some sort of contagious fungus that's affecting all of them. But if I assume independence here, then I can say x is distributed binomially with an n of 20 and a p-value of 0.1. And that's assuming that, if I'm only looking at 20 apples, my probability of success is 0.1. Success would be a bad apple in this case. Okay, so if I'm trying to find the probability of the batch getting rejected, that would basically mean looking at the probability, or it would be rejected if more than one of the apples was bad. So if I accepted, it would mean that x would have to be less than 1. And so I'd be using a binomial distribution here. With a binomial distribution, we don't need to change to a z-score, but I do need to remember that because it's discrete, I have to adjust my my inequalities so that they're always less than or equal to. So this is going to be the same thing as the probability that x is, if I'm looking at less than 1, then there's only one outcome it could possibly be, and that would be the probability that x is equal to 0. So if I go into my binomial, since it's an equal sign now, I'm going to go into my binomial CDF. And remember, we enter our n value first. In this case, it was 20. Our p-value in this case is 10%. Remember, I changed it. The x value that I'm interested in is 0. And if I find the probability would be about 12% of the time I would be accepting a bad shipment of apples. So I did change this problem just to make it work, because if I'm dealing with a binomial distribution, I wouldn't be able to have an x value that's a decimal. So trying to take 8% of 20, I wouldn't get a whole number, and my binomial calculations wouldn't work. But I did want to just kind of show you, since we did that with a means of taking a single individual from the population, what we do if we were dealing with small samples in a binomial setting or in a sample proportion setting. Okay, last problem. Sorry, I know this is lasting a lot longer than I expected it to because of the fire drill. Number 7 says carbon monoxide emissions for certain kind of car vary with a mean of 2.9, I guess that's grams per mile, and a standard deviation of 0.4 grams per mile. The company has 80 of these cars in its fleet. What's the probability that the mean CO2 level or CO level for the company's fleet is between 3 and 3.1 grams per mile? So in this case, I think it's pretty obvious, since we're given the mean and the standard deviation of the population, that we're dealing with a mean situation. Okay, and so if I'm looking at a sample of 80 cars, so if n is equal to 80, and I'm looking at the mean CO2 level for the sample, I'm dealing with X bar. So let's go ahead and define it. It's the mean CO level in sample. Okay, so let's find the mean of X bar. The mean of X bar is just going to be the same as the mean of the population, which is 2.9. Remember, when you're dealing with means, you need to include those units. My standard deviation of X bar, this is just going to be the standard deviation of the population divided by the square root of my sample size. And when I do this calculation, I get 0.0447. And that again would be grams per mile. Okay, and in this case, and actually let me just write real quickly. If I'm dealing with that standard deviation formula, the condition that applies would be to assume that my population has at least 10 times my sample. So we've got to assume that there are at least 800 cars in the fleet. The other thing we want to double check is, in order to use a normal distribution, we have to make sure either the population is normal, and it doesn't tell us about the population. It gives us the mean and the standard deviation, but that doesn't necessarily tell us that the population is normal. In this case, I can use a normal distribution because my n is 80. My sample is 80, which is greater than 30. And so that means that X bar is approximately normal. And if you want, you can say X bar is distributed normally with a mean of 2.9 and a standard deviation of 0.0447. And so the question we're trying to find is the probability that our mean is between 3 and 3.1. And so make sure that you're using appropriate notation here, so that we're talking about X bar because it's representing a sample mean. When I standardize these values, I get a z-score of 2.236. And that's going to be less than or equal to z. And it doesn't matter if you have the equal signs or not, because with a normal distribution, it doesn't matter. And then my upper would be 4.472. And that probability is 0.0127. Okay. And so again, you want to make sure that you, let's see. All right, so we want to make sure that we define our variable, that we state our mean and our standard deviation. Make sure you include those units, the condition for using the standard deviation formula, the condition for being able to tell me that X is approximately normal, and then when you're calculating the probabilities, you need to have the 3 parts like we have for all of the others. So hopefully that this kind of filled in any missing links that you guys still had. I apologize that you had to wait for me to deal with the fire drill. But hopefully this was helpful, and obviously come on in if you have any questions.